And we have new options in the design for seawater reverse osmosis by manipulating system flux. Very good. And I forgot to tell you that Robert is also a co-founder of Nano H2O. We are going on with the next lecture. I think it is addressing a thing we have with seawater reverse osmosis, that is the brine. And pellet softening could be a technology to help to reduce the items and issues around the brine disposal. And Mr. van Houwelingen, he will tell you about it. Yeah.
Well, good morning, ladies and gentlemen. I'd like to tell you something about technology that has been developed here in the Netherlands, to a large extent right here in Amsterdam, and also Eric Baars of Waternet here in the audience was to a large extent involved in that in the pilot plant work. I've worked with applying that technology in a number of different situations at OAS, and it is applied for water softening as it is in Waternet in Amsterdam. What I would like to discuss with you is the potential of this technology as an application in combination with RO. It's used in inland desalination, so not on seawater desalination where we have very high salt concentration, but in inland desalination where we generally deal with brackish water with lower salt concentrations. And I've produced this paper together with a number of people I've worked with in the past. With Rick Bond of Black & Veatch was involved in an AWRF, now WRF research program. Kim van Schagen of my company DHV, that was involved in together with Waternet in developing model-based control. And Tom Seacord of Corollo Engineers in the States, with whom we are currently doing a number of pilot plants in California, a bit south of Los Angeles. Now I'll drop right in with the conclusion, so to give you an idea that where we're heading in this presentation. I'll show you that pellet softening is an important tool in inland desalination, and mainly because it's very efficient in a number of different ways, both in terms of water consumption, in terms of chemicals consumption, in terms of space requirement, and also in terms of silica removal. And that is something that has been developed, has been found in relatively recent pilot plant trials. And in doing that, we found that especially in inland desalination, in where we're treating waters with higher calcium concentrations that we usually see when we apply the same technology for softening, we find that you produce lots more pellets out of the same cubic meter of water, and the control of your fluidized bed becomes more critical. And there, model-based control can really achieve an important improvement. So first I'll take you briefly through the pellet softening process. Then I'll focus on two applications: as a pre-treatment before RO, as treatment of the concentrate of a primary RO, and then the goal is to be able to take it through a secondary RO and squeeze a bit more water out of it. And then I'll go into the role of model-based control. So what is the trick of pellet softening? It is softening in an upflow fluidized bed reactor. The hard water enters at the bottom. We dose a base such as caustic soda or lime to it. As a result, calcium carbonate gets supersaturated and crystallizes on sand grains that we dose into that as a seed material. The main difference with better known sludge softening processes is that we apply a low supersaturation, and as a result we do not get crystallization in the water phase, but we only get the crystallization of calcium carbonate on the grains that we present in the fluidized bed. So in order to achieve that, it's basically a trick of creating better competition conditions for crystallization on the surface than in the water. One of the tricks is provide a high specific surface, and the other trick is provide a low calcium carbonate supersaturation. What are the differences with sludge processes? We don't remove magnesium in this way. We apply a high superficial velocity of about 100 meters per hour compared to 5 to 10 meters per hour at most in a sludge softening process. And we produce dry pellets instead of a wet sludge that still needs dewatering. I'll give you an example of pre-treatment, and that's an example that dates back a long time to the 1980s, when in the Qasim area in Saudi Arabia, groundwater desalination was applied basically as a temporary option until they would provide a main ring road where they would provide desalinated seawater also to areas inland. And basically the idea was to have this system in the Qasim area, mining the groundwater that was present there until the whole system would become available. And after that it would remain as a kind of standby system. The demands that were given there were an overall water recovery of 99% and an RO recovery of over 90%. Now with the water quality present there, that wouldn't be possible. So what we did there was apply pellet softening before the RO, with the filtration in between. In the pellet softening we took out the calcium, and in that way we could operate the water at the RO at a higher recovery. So what you see here, the main thing is that applying the pellet reactor here will allow you to increase your recovery from 80 to 90%. Then for a very long time inland desalination didn't get a lot of attention until a few years ago. It got attention in an AWARF project in the United States, where the focus was on zero liquid discharge. So very similar to the Qasim problem. How do we produce water with as little liquid waste as possible? And why did they need that desalination in that situation? Well, for some strange reason, the highest population growth is projected in desert areas in the United States, desert, arid or semi-arid areas. Here you see the forecasted population growth in those areas, which will result in growth of the water demand as well. And at the same time, you see that the main water source there is the Colorado River, which is getting lower and lower, as shown in the two pictures. And also by the water that's used there, you see a salinity increase. Millions of tons of dry solids accumulate in the ground and surface water in these regions. Well, what's the idea of zero liquid discharge? The idea there is to treat your concentrate in such a way that you get only solid waste out of it and squeeze more product water out of it. What are the established ways to do that? It's basically boiling these brines, so thermal processes in brine evaporators, expensive and extremely energy intensive. And then you end up, because you cannot get solid salts out of these evaporation towers, you still have to send the last bits to evaporation ponds, which are expensive, and basically use solar energy then to evaporate the water. but still in these areas where you have these arid conditions, you'll still need large areas to get rid of this water, and again you lose valuable water. Now, what was the technical approach in this project? It was to start with the primary RO and then check how you could treat the brine of this primary RO to allow to treat it again in secondary RO and squeeze more water out of it. So first they started to check what's the most efficient method of treating the concentrate of the primary RO. Then to check, does it allow further treatment in a secondary RO? And finally, if they've solved these technical issues, what is the cost picture in comparison to the old system I just described to you? They worked with a number of utility partners with completely different types of water. You see the wide range in TDS, and also the range in objectives that they were looking at. And especially you see that there is a number where the recovery of concentrate is important. I'll get to that in one of the projects that were applied after that. So what they did was to work together with computer modeling, bench scale testing and pilot testing at one facility, that was at the water supply of Las Vegas, and check which zero liquid discharge process would give the best results. And what I found pretty soon was that they would need some kind of softening, and then basically there was a competition between is a fluidized bed crystallizer with pellet softening or conventional sludge softening, the preferred option. Now what you see here in red are the results of pellet softening for calcium and barium, and in blue you see the results of sludge softening. And if you look at the two arrows, what you can basically see that you can achieve the same calcium and barium removal with pellet softening at about 2 pH units lower than you would need at the conventional sludge softening. So that will result in the reduced use of chemical, and that's basically what I say. In sludge softening you will also take out the magnesium, and because of the higher solubilities of magnesium sulfate and carbonate than of calcium sulfate and carbonate, you actually don't need to take out the magnesium to allow a higher recovery of your secondary RO. So in that sense you are basically wasting chemicals on magnesium removal, and that's an important advantage of a fluidized bed crystallizer. Here you see the picture of the comparison between the system with a crystallization unit on the left and against the old system with just a one-stage RO, brine concentrators, and then an evaporation pond. So you see there's a huge difference by at least a factor 2, and it's sometimes even a factor 5 to 6. So what they concluded in that research project, it is that pellet softening is basically the preferred technology for concentrate treatment, both in terms of the cost and in terms of the percentage of water that you can recover. It is efficient in calcium and barium removal, and more or less as a surprise we also found that you get some silica removal as well. Well, after this project, a number of projects were started in Southern California. Here we go a bit south, or from Roberts we go south of Los Angeles in Arlington, an area that is currently seeing a strong population growth. They already use desalination of groundwater for water production, And what they do with the brine from a number of towns just south of LA is that they transport the brines through a common brine line to the ocean, which is about 110 kilometers away. And currently that brine line is at its capacity. So the only way in which you can increase your water production is by increasing your recovery at the same time. So if you want to use twice as much water, you can only still discharge the same amount of brine, so you would have to increase your recovery from, let's say, 80% to 90%. Well, what you see here, and I've just highlighted the most interesting figures in red. What you see is important here, that you can also achieve about 40% reduction of your silica, together with the reduction in calcium and bicarbonate and barium that you would expect to see. The removal ratios for efficiency for calcium and barium are often very similar. This allows you to increase your recovery here from 82% to between 90 and 95% overall by applying that secondary RO to treat your brine. What was a very interesting thing that they saw in this, found in this program, they operated in batches. So at the start, in operating this pellet softener, they saw a very high turbidity, over 500. Within a couple of hours, it reduced to a stable situation at around 100, and then after that, it rose up again to over 500 rapidly. So what you see there is the importance of the pellet diameter, because what they did, they started with a fresh batch of sand. So at the left-hand side, you have very small sand grains that expand a lot, and in the reactor you have relatively low specific surface. Then you get to the optimum pellet size, and that gives you some expansion and a lot of surface because the pellets are relatively small. At the right hand side you have very large pellets that are so large that you only have little specific surface. Now the way that we can solve that was investigated here in Amsterdam in the PROMISET program, and that's by applying model-based control. They applied a number of models that show both the effect in which the calcium and carbonate concentration in the water is reduced from the bottom of the top to the reactor. At the same time, the sand grains travel in the other direction and develop a scale of calcium carbonate around that. Now, I won't get into the details of this, but by using this and checking this, what you do, you can get a better design of your control system. Now what you do then is have to determine your objective. In our case, that is reducing the chemicals demand, determine a number of operational restrictions, often hydraulic in our situation, and determine the most serious disruptions. And what we found in Arlington is that the most serious disruption in this particular case is pellet size. So if you're able to control this pellet size, then you could improve your whole operation dramatically. And then the trick is, how should it be controlled? Well, in that program executed here at the waste particle plant, it was found that the differential pressure over the bottom half meter of your fluidized bed gives you an excellent direct indication of the pellet size in that area, and in that way of the specific surface area that is available for crystallization, and that can help you to reduce the demand of chemicals and also reduce the formation of carryover from the reactor. Which takes us best back to the conclusions. I hope to have demonstrated to you that pellet softening can be an important tool in inland desalination because of its high efficiency both in water recovery, in chemicals consumption, in space requirement, and that it can also remove some silica. And if you really want to apply it, then optimal management of the fluidized bed is of the utmost essence, and controlling that in a good way can be achieved by model-based control. Thank you very much for your attention.
Thank you, Gerard. This is a nice example of hybridization of, say, two technologies existing already for many years in our business.